Welcome to VW 9.3. Today we'll be talking about a pretty cool concept called inverse functions. So first, here's our first example. Determining whether a function is one-to-one. Determine whether the following functions are one-to-one. So quickly we have to define that. One-to-one is basically a function where every input has one output and every output has one input. So think of it as a function, but it's even more strict. Every input has an output, and every output has only one input. So if I look at this one, 38 goes 57, that's fine. 42 goes here, 46 goes here, 55 goes here, 61 goes here. So this would be considered a function, because a function means every input has one output. However, this is not one-to-one. And it's not one-to-one because this output right here is going to two different inputs, which is not okay. So this cannot happen. But still note, this is a function, just not a one-to-one function. So if you have an example like B, you can organize it a little bit differently. You can kind of do these circles right here. -2, -1, 0, 1, 2, 6, 3, 2, 5, and 8. And let's map it. -2 goes there. -1 goes there. 0, 1, and 2. So this would be considered one-to-one. And also notice this is definitely a function as well. So all the things we'll be dealing with today, though will be functions, we're just wondering if they're one-to-one. And we can see again this nice one-to-one pairing here. So now it says for each graph, use this graph to determine whether the function is one-to-one. So let's think about x squared. Let's just sketch it. That would look something like this. Now graphically what we do is this. We use a horizontal line test. You might recall the vertical line test. The vertical line test will test if it's a function. The horizontal line test will test if it's one-to-one. So I can see right here, it hits it in two places, so this fails the horizontal line test. Meaning it is not one-to-one. So this next one, x cubed, let's try to sketch it here. Something like that. You can see that no matter where I put this line, I'll only hit one spot, which means this is one-to-one because it passes the horizontal line test. So now let's go to the next part of this. Now it says verifying inverse functions. So inverse functions we'll talk more deeply in class, but for now think of them as a function that will undo a given function. So it says verify that x cubed is the inverse of cube root x. So really notice what this is doing, right? This is cubing x. This is the cube root of x. So they would definitely undo each other. So intuitively, we can see that they are in fact inverses. Now to verify it algebraically, let's see what happens. We are going to plug g inverse into g. So that would be g of the cube root of x. And let's look at what happens here. Cube root of x cubed, you get x. So notice how it completely undid everything, and you just got x back. And if I do g inverse of g, g is x cubed. If I do the cube root of x cubed, I do get x. So notice how working through all this, you just get back to x. At this point, we can conclude g and g inverse are in fact inverses. So that's how you prove it algebraically. So now let's look at a more complicated example. It says verify that these are in fact inverses. So we're going to plug them into each other like this. So f of 1/2 x minus 3. Let's see here. So 2 times 1/2 x minus 3 plus 3. This is kind of cool. The 1/2 and the 2 cancels out. Then we're left with x minus 3 plus 3. And look, we did get back to x. And if I flip it around, f inverse of f, that would be 1/2 times 2x plus 3 minus 3. The 3's cancel out, and that's clearly x. So therefore, f and f inverse are in fact inverses. So to verify it, notice what we're doing. All we're doing is we're just plugging this one into the other one and this one into this one. And we're just checking that you do in fact get to x. That will prove that they're inverses. Next example says graphing the inverse function. It says the graph is that of a one-to-one function. So notice how this is definitely one-to-one, so pass any horizontal line test. What it wants you to do is draw the graph of its inverse. So there's a really simple way to do this. What you do is you switch your x and y values. So look at this. This is -2, -1. So the inverse is going to be -1, -2. This one is -1, 0. So you write 0, -1. This one is 2, 1. So 1, 2. And then sketch. And right here is the graph of your inverse function. And what's really interesting is you might notice that there is a line of symmetry happening right here. This is y equals x. So what happens is that, put a big star here, f and f inverse have symmetry over the line y equals x. Okay, so now we're going to do a few more complicated examples to make sure we have this down. It says find the inverse of f of x equals 2x plus 3. Graph it on the same coordinate axis. So to do this, let's first just graph 2x plus 3. That's pretty easy. I know that's right here, 3. Then go over 1 up 2. So there's our line 2x plus 3. Now we just learned how to graph the inverse. The inverse is pretty easy, right? Because we can just flip the points around. So if this is 0, 3, I should be at 3, 0. This one is 1, 5, so I'm going to graph 5, 1. This one is 2, 7. I'm going to graph 7, 2. And I can see the line appearing right here. So there's our f inverse. And again, we're seeing, right, that line of reflection again. Here's the line of reflection. Y equals x. That's a pretty easy way to graph it. Now I want you to also do it algebraically. So if you look at this thing, f of x equals 2x plus 3. The way you find the inverse algebraically is you simply switch x and y. Because if you think about what we're doing this, I got these points by just flipping the x and y coordinates. So I'll do the same thing algebraically here. If y equals 2x plus 3, you switch it, so x would equal 2y plus 3. Now solve for y. So 2y should equal x minus 3. Divide by 2, so that'd be 1/2 x minus 3 over 2. Therefore, f inverse x is going to be 1/2 x minus 3 over 2. And there's our algebraic inverse, and we can see this does in fact match the red line right there. And just for good measure, let's do domain and range. So this is the way we're going to do domain and range for these, and it'll make more sense in a little bit why we do it in this particular way. I'll put it right here. So this would mean domain of f. This is the range of f. So this is pretty easy because I can see that for all of them, it's all real numbers. So there's not really much to do here. So I'll just put these everywhere. Let's go to our last example. Find the inverse of x squared minus 4 if x is less than or equal to 0, graph in the same plane. Okay, so let's just work on the graph first. X squared minus 4 is a parabola. And this is what most of you would do, right? -4 is our y-intercept, 2 and -2 is our x-intercept. So you know it's something like this. I'll make that a little bit nicer. Now, as we're graphing our parabola, a few of you might have noticed this is already an issue. This is not one-to-one. Because up here, remember we spent all that time saying one-to-one functions, one output, one input. And we can see here, this fails a horizontal line test. This is where it all kind of comes together. In order for f inverse to exist, f must be one-to-one. So that was the purpose of doing all that stuff for one-to-one, is that you can't actually have an inverse if it's not one-to-one. So that's why, if you look right here, this stipulation is there. Because currently this definitely fails a horizontal line test. But if I limit it to this domain, I can get rid of this part. And now this is okay. That will pass horizontal line test and I can do the inverse. So let's try it. If here is f, let's flip the points around. This is 0, -4. So next one's going to be -4, 0. This is -2, 0. So I want 0, -2. And then it should look something like that. So there's our inverse function. And again, I can kind of see my line of reflection here. So definitely it's working. So before we do domain and range, let's actually do the algebra, because algebra is kind of interesting here. You have y equals x squared minus 4. If you switch it, you get x equals y squared minus 4. So notice how the squared stays. You simply switch x and y. And now we're going to notice something kind of weird. Move this over here. When I solve for y, I get x plus 4 equals y squared. When I root everything, absolute value of y equals the root of x plus 4. Remember that this absolute value is going to create two situations. It's going to create plus and minus root of x plus 4, which means it creates two answers. This is why this one-to-one part is important, because you have to know which function it would be. You can't take both of these, because if you graphed both of them, you would get this part of the parabola here, which would make the inverse not even be a function. So that's why this stipulation is here, because you have to know which one to pick. And if you look at this, it says x is less than 0, which means we want the negative side of the parabola. So we don't want this one right here. Cross that out. Our conclusion is f inverse must be negative root x plus 4, which matches right there. Now this final part is where everything is going to finally come together, for domain and range anyway. If I look at the domain of f, that's this one, it was told to us, right? Everything less than 0, so negative infinity to 0. Now, let's do the range, so I can see right here, that would be -4 to infinity. And actually, I want you to do that in a different color. Let's do that in blue. And now, look at the inverse function, this red one. Look at the domain. That's -4 to infinity. I'm going to do that in blue as well. And then, look at the range of the red. That would be -infinity to 0. I did that in that color because you might notice something. Notice how these are the same. And notice how these are the same. So that's pretty crazy. So the domain of the original becomes the range of the inverse, and the domain of the inverse will become the range of the original. So this gives you a way to easily find the domain and range of everything if you have f and f inverse. And this should make total sense because remember how we do inverse functions over here. You switch x and y values. So I know that was a bit complicated. If you have any questions, please let me know in class and we can talk more about it.